Hi, in this video I will be explaining how a message can be sent from one node to another through the use of various entities in different layers. This diagram over here illustrates the layer model for the protocol used in this project. Over here we have the Jupyter Notebook set up so that we may illustrate the layer model in action. As you can see here, we have the Alice node representing this side of the diagram, and over here we have the Bob node representing this side of the diagram. Once Alice sends a message to Bob, as you can see here, we have the LEE, which would be the application layer entity, and then we have the DLE, the data link entity, which corresponds to this one over here, and the LEE, ALE to this one. And over here we have the PLE, which corresponds to the physical layer entity. And this one over here sends the message directly to the PLE2, which corresponds to PLE Bob. And then the PLE Bob forwards the message to DLE Bob, and then that entity forwards it to ALE Bob, which is the receptor from over here in the communication. Over here from whenever Bob sends a message to Alice, we can see the same protocol going on. You see over here, Bob to Alice, that's a message sent from Bob to Alice, and it starts at ALE Bob, and then moves over to DLE Bob, and then to PLE Bob. From there, it moves over to PLE Alice, which would be over here, and then forward to DLE Alice, and finally to ALE Alice. Modify the PLETR class as the exercise specifies. More specifically, we modify the delay time in the looptx function from 1 second to a random time delay from 0 to 2 seconds. And we also modified the packet loss probability from 20% to 10%, and added the duplicate probability of 5%. And over here we ran a simulation, and as you can see is from Alice to Bob once again, and then we have Bob to Alice over here. And Alice, this is this is modified to simulate 10 messages from Alice to Bob, and as you can see here is for messages labeled from 1 to 10. And as you can see, we start off at ALE Alice, and move over to DLE, then to PLE. If we continue moving forward, we can see that we have a duplicate packet generated here, and if we continue over, we see that we have another packet lost generated over here, and another one over here, and so and so. If we go ahead and write Bob to Alice over here, we can see the simulation in real time. As you can see, there was a packet lost over here, and it's updating since the delay time was changed. Messages are being outputted at different times. As you can see, another packet lost over here. Oops, sorry about that. And we continue seeing the output live. Another packet lost, and so and so. This was because we modified modified the probability of the package lost and the duplicate packages, as well as changed the delay time. So for the last part, a minor modification was made to the PLTR class. More specifically, whenever a packet is lost or duplicate, it will send a message notifying that the packet was lost or duplicate, so that we may keep track of these events. In reality, this would not be like this. This is just a simulation for the sake of the video and the demonstration. So over here in the MLETR class, we have the constructor over here. It will take a lower entity, transmitter receiver. It's the messages to send are 20 for the sake of the video. For the experiment and the report, it's 100. And over here we set up the we initialize the button using the widgets packet we import over here. And then the click handler, which will send messages according to the variable declared over here. And then that message will contain the experiment ID, the message ID, which is just the index of the message, and the transmission time. As you can see here, we send it with the lower entity and then assign the click handler to the button. Over here, we have the loop RX function or method. It uses a previous delay variable to keep track of the delays. And over here we set up a messages to receive variable assigned to the messages to send. This is to keep track of once all the messages were sent and received. Over here we see if messages to receive equals 0, this means that all messages were received, therefore display the measurements for that communication scheme. Afterwards, reset that variable to messages to send once again and reset all the other instance variables to 0 so that we may keep track of new messages or a new procedure. Afterwards, we receive the message over here, and if the message is packet lost, as I mentioned previously, we changed the PLETR class so to send a message packet lost if the packet was lost, and duplicate packet if it was duplicated. Over here, as you can see, we are keeping track of how many packets are lost and how many packets are duplicate. If none of these options occur, then we will extract or parse the time from the message. As you can see here, time and then the quantity over there. So we want that specific quantity, so we split it using the delimiter time since we know the message content. Afterwards, we have the transmission time, which would be the time that the message was transmitted, and then the receiver time, which would be the message, the current time once the message is received. Afterwards, we subtract this from receiver time from transmission time, and we would have the current delay time. And to that, we subtract the previous delay to have just the specific delay of that transmission. And we update previous delay over here to continue keeping track of that so we may use it in the further iterations. Over here we are updating the messages to receive so that the method will know once the messages all the messages are received, then it will use the display measurements method, which brings us over to that method, which basically what it does is it calculates or computes the average delay time using the delay time method we declared over here. I'm sorry, the delay time variable we declared previously. The messages to send, which would be a constant variable declared on the initialization. For this, again, for this experiment, for this video demonstration is 20, but for the actual experiment was 100. And as you can see here, it prints out the node-to-node measurements for this takes for how many messages was the transmission, and then the average delay time for those many messages, the average message loss rate, as well as the message duplication rate. So without further ado, I will begin a demonstration. I have already ran all the boxes, so we'll click over here and begin the demonstration. As you can see, these are the measurements for 20 messages. The average delay time was 1,952 milliseconds. That's almost 2 seconds. The average message loss rate was 10%, 0.1, and the average message duplication rate was 15%, 0.15. For the next experiment, which is the second one, we basically have the same scenario, but with the data link entity in addition. And I already ran the experiment, and as you can see here, the output was the average delay time was almost 9 seconds. The average message loss rate was 7%, and the average message duplication rate was 5%. This is counting for the data link entity layer, which it's more adds more overhead to the average delay time, as you can see over here. So basically, that is my implementation of the MLETR class. I hope you enjoy this video demonstration, and thank you very much for your attention.